Okay, scholars, so what I thought we would do is kind of take a quick review of rotation, what we know so far. So you guys have two skills, hopefully right now. Rotational kinematics, understanding the kinematic equations and concepts that go with rotation, rotational velocity, rotational acceleration, etc. And you should be able to write an expression for the rotational inertia, also known as the moment of inertia, for an object. I'm not sure if we got to work through this example before the break, so I thought we would go ahead and try it. We want to find the rotational inertia of this object where we have a rigid rod whose length is L and mass is M, and it is attached to the inside of a thin hoop whose mass is also M, and you can see its radius is L over 2. So I just wanted to give you a quick trick. Whenever you're trying to find the rotational inertia for a compound object like this, an object that is really made up of two objects, a rod and a hoop, for example, it's just going to be you adding those two things together. So it's going to be the rotational inertia of the rod plus the rotational inertia of the hoop, just like that. So if we can find each of these, we can add them together, and boom, we're done. So let's start with the rod. We've done this several times. And the axis of rotation is right here. That's always going to be the first thing you do is find the axis of rotation for the system in question, because everything is defined based on that. Remember, the equation for moment of inertia is the integral of r squared dm, where this has a specific meaning, right? It means every little tiny piece of mass based on how far it is from the axis of rotation. This r is the distance that that little mass piece is away from the axis of rotation. So you have to first identify the axis of rotation. So if here's my rod, there's the axis of rotation right in the middle. And I like to first identify my little mass piece. So there could be a mass piece dm, just like that. And already we're thinking that we're going to have to relate mass to location, to position. So I'm probably going to have to use density to do that. Linear density is big mass over length. This thing has a length of lowercase l is what they've told us. And I know that's going to be the same ratio for little tiny mass and little tiny length. But here my little tiny lengths, because this is along the x-axis, I can just call that a dx. So I can say that dm equals lambda dx, just like that. And now I'm ready to integrate. I'm basically integrating all these little tiny masses from, maybe you want to call this a length of negative L over 2 to positive L over 2, just like that. So I can say that the I of the rod is going to be equal to, I'm going to pull the lambda out, the integral of x squared dx, where lambda dx is dm, and I'm doing this from negative L over 2 to L over 2. And I'll leave that calculus up to you, but it ends up being equal to 1/12 ml squared, just like that. So now I know what the I of the rod is. It is 1/12 ml squared. Simple enough. Now let's do the hoop. This is really simple because all my little mass pieces dm in this hoop are the same distance away from that axis of rotation. They're a distance of L over 2. In this case, that's the radius of my hoop. So because they're a constant distance away, my integral just becomes this. That r squared becomes a constant. Remember that r is the distance away from the axis of rotation that my little mass pieces are, and that's a constant L over 2. So I can pull that out, and I'm going to get L squared over 4 times the integral of dm. And the integral of dm, when you add up all the little mass pieces, is just mass. So the I of the hoop then is just 1/4 ml squared. Oh, whoops, I wrote that down wrong earlier. That should be 1/12 for the rod. So sorry. 1/4 ml squared, and now I can just very simply add these together. 1/12 ml squared plus 3/12 ml squared. I'm going to get 4/12, which of course is 1/3 ml squared, and that is the overall moment of inertia, rotational inertia for this object. Yay, not too bad. So the big lesson there is that whenever you have a compound object like this rod hoop system, treat each object in that system individually and then just add them together. Hero, you are fine, Papa. Okay, I thought that we would do one more because we need to practice this quite a bit. We've done a hollow sphere, the eye for a hollow sphere. Let's do one for a solid sphere. Okay, so here's my solid sphere, and let's say that I want to figure out its rotational inertia as it rotates about the x-axis. So it's rotating about its center, where I'm defining that across the x-axis. All right. So let's remind ourselves the equation: I equals the integral of r squared dm. And let's see if I can draw a little dm, a little mass piece here. I really have two options, and this is just something that you're going to have to get used to, how to break down your extended objects into little pieces. I can treat this like a gobstopper, like an onion. I can see that it has layers of individual little shells, like an infinitesimal amount of, an infinite number of little infinitesimal shells working out from the center. That's one way of doing it. Another way of doing it, and this is the way that I prefer, I can show you both ways if you like. The way that I like to do it is I can treat this thing like a series of disks. So this could be a solid disk like coming out at me and then going into the screen. And let's see if we can characterize some things about that disk. Let that be x equals 0 right there. I can say that that disk has a height y, and I can say that it has it has a radius y, right? It's going to be some y value, and it has a thickness right here, dx, some infinitesimal value of x, right? So we may be able to try to write this expression, but I'm going to show you that if you try to start with this, you're going to end up getting fooled, and you're probably going to make a mistake. Let me show you why. So I've already said that I'm treating this like a bunch of little disks who have radius of y and thickness of dx. So I might be tempted then to call this disk my dm. And so I can come over here and use the concept of density, volume density. The Greek letter rho represents a volume density, where that's mass per volume. The volume of a sphere is 4/3 pi r cubed. I'm using big R to represent the radius of the sphere. And I know that's also going to be equal to dm as a ratio of dv. So I can rearrange this, and I can say that rho dv equals dm. And then I might be interested in putting my dv in terms of something else. Because remember, ultimately I'm trying to get like just one variable that I can integrate with respect to. So dv will be like the little tiny volume of this. So what's the little tiny volume of this thin disk? Well, it's area times width, right? That gives you volume. What's the area of the disk? Pi r squared, where the radius of the disk is y, and the thickness is dx. So I'm going to get rho pi y squared dx equals dm. Okay? So now I have a problem. I need to get y in terms of x so that I can, actually integrate. That's not going to be too complicated. Let me draw another disk right over here to show you how we can do this. Let's say that it has radius of y, and let's say that this is some x value going across here to get to the disk. Well, I know that this is a right triangle whose hypotenuse is r. And I kind of wrote over that. Let me fix that real quick. So I can make an expression for this right triangle, x squared plus y squared equals big R squared. And then I can put y in terms of x. I can say, therefore, that y squared equals r squared minus x squared. And I could plug that in for this y squared. And that would put dm in terms of one variable and integrating with respect to that variable, right? The problem is with this approach is, what is this little r value here? So I've fleshed out my dm, right? My dm is going to be rho pi. We've said already that y squared is this, r squared minus x squared dx. So that's what dm is. I have x and dx, but my r value is what? Well, here's where you're going to make a mistake, and here's where this whole thing falls apart. This r value is, remember that this integral says, hey, we want to find each mass piece in terms of how far away it is from the axis of rotation. But the way that we've identified our little mass pieces, there's no simple way for us to flesh that expression out. In other words, you may be tempted to substitute r with y because you think, oh, that's the radius of my little tiny mass piece, right? So you may be tempted to substitute r squared with this y squared again. And unfortunately, if you do that, you're going to get a wrong answer. Here's why this approach does not work. Once again, this integral is saying, take each little tiny mass piece and write an expression for how far away that little mass piece is from the axis of rotation. Well, because we've treated our masses as these disks, and we wrote an expression for their tiny little mass, their dm. So here's the mass of a little disk piece in terms of position and density. That is not truly going to get me anything for which I can write an expression that would give me how far away that little mass is away from the axis of rotation, because I've written an expression for the mass of the disk, and that is not at all going to get me how far away a little mass is from the axis of rotation. In order to do that, I would have to think about all these little mass pieces and how far away they are from the x-axis, which is my axis of rotation. I have talked about the entire disk here. So this is not going to work for me for that reason. This integral I'm doing is not truly adding up all the little mass pieces based on their location from the axis of rotation. All it's doing is talking about what that little mass of that disk is, but there's no way now for me to relate that to how far away that is from the axis of rotation. So unfortunately, this is not a great approach. There's a simpler thing that we could do, and it is this. Instead of looking at this using the classic definition of I, what I can do instead is say that my I value for the entire object is going to be the integral of the I value for each little object. Let me say that one more time. The simplest way of doing this, the simplest way of doing like a big extended object, the first thing that we're always going to do after we define the axis of rotation is try to think about what my little dm piece is. And we've said one really simple way of doing that is view this as a bunch of really thin disks. Well, if I view it as a bunch of really thin disks, I can write an expression for the I value for each little thin disk that would be di, an infinitesimally little bit of I, the rotational inertia for each little disk. And then I can integrate that and get the rotational inertia for the entire thing. Okay, so that's going to be the approach that you're going to want to take rather than doing this, because that's going to be really difficult and it's gonna screw you up. So all we can do is say, hey, I'm treating this sphere like a bunch of infinitesimally thin disks. Let me just integrate the rotational inertias of all the disks, and that will give me the rotational inertia of the sphere. Okay, does that make sense? So taking that approach, let's see what we can do. Now this is going to require that you know already, this is the only, I guess, downside to this, that you know already what the DI is. In other words, DI is going to be the I value, the rotational inertia for a disk. So how can we get the rotational inertia for a disk? Well, maybe you have memorized it, but if you have not, then we can come down here and do a disk real quick. So let's think about what the I value for a disk is. So I'm just going to draw a disk. I'm looking at the front of the disk, obviously, and I'm going to say its axis of rotation is there in the center. And let me draw a little dm piece for the disk. I can treat the disk as if it is an infinite collection of little tiny rings. So I'm going to use density. Sigma is equal to mass over area for the whole thing. So this thin disk has, a big radius, big R. So its area is going to be pi big R squared. And then from a small point of view, my dm, what area does that dm have? Well, let's think about this. If I were to cut that and unroll it, it would form a line. I think we've done this before, but it's good to go over again. So this is me cutting my little ring here, unfurling it, and it's going to have a length of 2 pi r. That's just the circumference of it. So I have some little r value in there. And then it's going to have a width of dr, an infinitesimal slice, an infinitesimal piece of r. So the area of each little piece is going to be 2 pi r dr. That is also just the derivative of this. Because really what we're doing is we're finding infinitesimal bits of mass per area. So the derivative of mass is dm, the derivative of area would be this right here. Okay, that's one more way of looking at it. All right, so my I value for the disk is going to be the integral of r squared dm. My dm, I can rearrange this and say, therefore, that dm equals sigma 2 pi r dr. Plug that in for dm. Now, this is a good expression. This expression works because my dm here is definable as a distance away from the axis of rotation, a distance r. Okay, so this is a fine integral to use because that's the meaning of it. So anyway, we plug in dm there. R is just going to be r, little r, the distance away from the axis of rotation to my little mass piece. And of course, I'm going to integrate that from 0 to big R. So it becomes sigma 2 pi integral of r, integral of r squared dr, evaluating that from 0 to big R. I will let you do that integral for yourself, but ultimately you get 1/2 mr squared. So that is the integral, that is the rotational inertia for a disk. So I can bring that up right here. Let me remind you what we're doing up here. We've said that the traditional approach doesn't really work for this because there's not a good way for us to write an expression for how far away each little mass piece is away from the axis of rotation, because our mass pieces themselves are disks about the axis of rotation. So instead what I can do is I can treat the sphere like a bunch of these little disks and say that the overall rotational inertia for the sphere is the integral of the rotational inertias of each little piece, where each little piece is a disk. So now I'm just trying to define di. Well, it's going to be the rotational inertia of each infinitesimally thin disk, and we've just discovered that is 1/2 mr squared. So that's going to be 1/2 dm is m, and then r, the radius of the disk, is y squared. And notice that I am kind of already good to go, because I need to put these now in terms of things that I can integrate, and I've already done that. I've already done that work based on my erroneous integration earlier. In other words, I need dm and y with I need to put those terms in terms of each other, and I really need to get them in terms of x, because think about what I'm doing. I'm integrating all these little disks from negative r to positive r, to x equals negative r to x equals positive r, right? So I need these things in terms of x values. Well, I already have that, don't I? I use the concept of density to get mass in terms of volume. And then I realized I could put volume, the volume of my disks, in terms of the variables y and x. Pi y squared would be the area, dx would be the width. Area times width would give me a little volume piece. And then I said, wait a second, I need to put y in terms of x, and I realized I could draw a triangle here for every single disk, and put the height in terms of how far away I am from x equals 0, based on Pythagorean's theorem with a constant r value. So this will always be true. Rearrange and get y squared equals this, and I plug that in and got an expression for dm. So I can put this right up here for dm, and then I also, again, I already have y squared in terms of x. So my di then is going to be this. It's going to be 1/2 rho pi r squared minus x squared dx times y squared, which is r squared minus x squared, and there it is. That is my expression for di. So to find the overall moment of inertia for this, I just need to integrate from negative r to r. And so my integral then will become I equals, I'm going to pull out all my constants, so 1/2 rho pi, the integral from negative r to r of, looks like I have this, so r squared minus x squared squared, because I have two of them, dx. I will let you guys do the calculus there for that. And I do encourage you to take the time to do that, and let me know if you have any questions. You may have to use U substitution. I don't know if you will, though. I think that you could just maybe FOIL this out and get a simpler expression that way. Anyway, your ultimate answer becomes 2/5 mr squared. So that is the rotational inertia for a solid sphere about an axis of rotation through its center. 2/5 mr squared. So remember what we did. The first thing that we tried to do was we defined the axis of rotation. That's always going to be the first step. The next step was to define what our little mass piece is, our little dm. We said that it's a disk. We realized there is no good way for us to use this classic definition of rotational inertia, because we can't write an expression for how far away the mass piece is from the axis of rotation. Because these disks themselves are about the axis of rotation, so we couldn't really do that. So instead we went to this, where we said, oh, well, I can just write an expression for the moment of inertia of each little disk and let that be di, an infinitesimally tiny piece of the overall moment of inertia of the overall solid sphere, integrate all those di's from negative r to r, because I'm integrating all the disks, and that'll give me my answer. And there is our answer. Nice. Okay, so real quick, I wanted to go over another method of finding the I value for a solid sphere. Remember last time we did it by looking at it as if it was composed of all these disks? Well, we can also view the solid sphere, as I mentioned before, as if it's composed of all these onion or gobstopper layers of infinitesimally thin spherical shells, hollow shells. So I can view the solid sphere as a collection of these shells going out from a radius of 0 to a radius of big R. So here I've drawn one of those shells, and I'm realizing that I can use this idea once again, where the overall rotational inertia for the entire sphere is just going to be the integral of all the tiny rotational inertias of all the tiny shells. So what I need to do now that I've identified this shell is identify its little tiny rotational inertia. So this requires you to either derive or know the rotational inertia for a shell. We've done that in the past. I'm not going to take the time to repeat it, but it's 2/3 mr squared. So my di then, the tiny little rotational inertia piece of each tiny little shell, is going to be 2/3. The mass is dm, little tiny mass, and the radius is little r squared. So what I need now is to get dm in terms of r, and of course I'm going to use density to do that. I have volume density. Mass per volume of the whole thing, and then a zoomed in perspective, little mass of my little shell and little volume of my little shell. Let me explain to you this piece right here. The volume of this shell, it's a thin, hollow shell, so you think it doesn't really have a volume. Well, its volume is just going to be the surface area of the shell times the thickness of the shell, where the thickness is a little tiny dr piece, a little tiny piece of r. So the surface area of a sphere is 4 pi r squared, and the thickness of each shell is dr. So that gives me a little dv, a little volume piece. So now I rearrange that, and this is, of course, is rho. That's that density here. I'm going to use the actual definition of it later. And I have dm in terms of r. So I'm able to plug that in here, my little di, infinitesimally small rotational inertia piece of the tiny shell, and I get this expression whenever I combine the dm here. And now I can just integrate that from a shell with a radius of 0 to a shell with a radius of big R. And it's a simpler integral than the one that we had last time. So I integrate that and I get this, and then I replace rho for what it actually means here, plugging in m over 4/3 pi r cubed. It simplifies to this, which then simplifies with the common common factor of 12 there. Simplifies to this, which is the answer that we got before. So this is another way of doing it. This one's actually a little bit simpler, where we break the object down into these infinitesimally thin shells, like an onion or a gobstopper, these layers, and we say, hey, each layer has a little tiny piece, contributes a little tiny something to the overall moment of inertia, and then we just define what the little tiny moments of inertia are, and we go from there. Of course, this is with an axis of rotation through the middle. I should have said that. All right. What if instead we were looking at a sphere whose axis of rotation was not in the middle, but was on an edge? So in other words, the sphere is rotating with respect to this axis, okay? With respect to a point through its edge. What would the moment of inertia be? Hopefully you remember how to find this. All we've done is we've shifted the axis of rotation, right? The axis of rotation was through the sphere's center. It was through the center of mass of the sphere, and now we've just shifted it down Looks like we've shifted it down by a radius, right? By a distance of r. So who remembers how we can do this? Yeah, we can use the parallel axis theorem, can't we? This is an important equation that is not going to be on your AP equation sheet. You do need to be able to do this. This gives you a new, you could call it I prime, you could call it I new, something like that. A new I value for when the axis of rotation has been shifted. It's going to be equal to the I value that is calculated when the axis of rotation does go through the center of the object, the center of mass of the object, and you're going to adjust it by a factor of md squared, where d is the distance that you have shifted the axis of rotation. Okay? So this is really simple. We know already that the I about an axis through the center of the sphere is 2/5 mr squared. We found that earlier. Okay, so all we have to do is add to that md squared, where d is the distance that we've shifted the axis. Well, my new axis is a distance r away, right? So I'm just going to add to that mr squared. And of course, you guys know how to add fractions. When we get this, we get a new answer of 7/5 mr squared. So that is the I value when our axis of rotation is down here on a point tangent, on a point of the edge of the sphere. All right, this is the parallel axis theorem. You do need to memorize this equation because it will not be on your AP equation sheet. Okay, notice that this answer makes sense. It makes sense that whenever we shift our axis of rotation away from the center of mass, that our I value will get larger. Remember what rotational inertia is all about. You guys do need to know this conceptually. Rotational inertia is kind of tells you how, it's just like inertia, right? So inertia for objects moving linearly with linear motion, things that are not rotating, is just mass. But we've said that for rotating objects, the mass is not all that matters. It matters how that mass is distributed with respect to the axis of rotation. That's how we define this thing. It is how is the mass distributed with respect to the axis of rotation, where this r value, of course, in the integral is the distance away from the axis of rotation, right? So if we shift our axis of rotation down away from the center of mass, we now have more mass located a farther distance from the axis of rotation, from this new axis of rotation. So we have more mass located a farther distance away. Of course, our I value will get bigger. The more mass you have located a farther distance away from the axis of rotation, the bigger your I value is, the more difficult it is to cause the rotational motion of that object to change. Remember, that's what inertia is all about. How difficult is it for an object to change its motion? For linear motion, that's just proportional to mass. That is mass, the mass of the object. For rotational motion, it is how is that mass distributed away from the axis of rotation. All right, so hopefully this was a good, helpful review for you in terms of looking at rotational inertia. What we may want to do now is go over some other examples. Okay, why don't we get ourselves caught up, back up to speed with some rotational kinematics. So here's an example problem for you. Let's say that we have a circular disk, and let's say that it is moving counterclockwise. So my omega is this way, and that's constant. So the omega is constant. And let's say I'm looking at 2 points. Let's say I'm looking at this point A and this point B right here as the thing is rotating. I'm going to draw some velocity vectors for those. So here's an instantaneous velocity vector, always tangent to the path, right? For point A, and then here's one for point B. Okay, so there's a scenario, And let's answer some questions about this. So question 1, I want to know which point has the largest linear speed, in other words, the largest v-tan. Hopefully you can answer this right away. What do points A and B have in common? Well, they have the same omega, where let me remind you that omega is d theta dt. The angle change with respect to time, well, those are the same for A and B. They're sweeping out the same angle, but because A is farther away from the axis of rotation, as it sweeps out that same angle, of course, so let's say that here's the angle that they've swept out. So you can see there that the angle is the same. However, in sweeping out that angle, object A has had to travel a much farther distance than object B did in the same amount of time. So of course, object A has to have the largest tangential velocity. Another way of doing that would be to use our translational equations to translate between the two worlds, the linear world and the angular world, and this is how you get between them. So the larger the radius is, where radius is distance from axis of rotation, the larger the v-tan has got to be. All right. Question 2, which one has the largest d theta dt? Which one has the largest angular speed? Well, of course, the answer is that A is equal to B because they have a constant omega. Simple enough. Okay, question 3. We place a coin at both points. So a coin is placed at both points. At which point, I think we've done this question like several times in this class already, but it's a really good one for you to make sure you know how to do. At which point will it fly off if omega is slowly increased? So if I put a coin right here at point A and a coin right here at point B, those coins will be moving on the disk in a circle. And remember, what is required for an object to move in a circle? We have to have a centripetal force, right? So I can label this here and here. Those would be my centripetal forces, my center-seeking forces, causing a centripetal acceleration. So what is supplying that centripetal force? What's the only interaction between a coin and the disk on which it's sitting that is working along the disk? Well, it's going to be friction, right? So basically the question is asking us, if we slowly start to increase the speed, where will friction no longer be able to supply the centripetal force? We're really asking which object needs a larger centripetal force. Well, this is quite simple. We know that a net centripetal force causes centripetal acceleration, also known as radial acceleration, right? Where that is equal to v squared over r. And this v here is the v tan. And so we already have thought through the fact that v tan is omega r. So we can see that the centripetal force at any given moment in time is just going to be equal to this. So if we are slowly increasing omega, they're both going to experience the same omega change. Omega is changing the same for both objects. By the way, if we're increasing omega, what do we have now? We have radial acceleration, right? So these coins are not just going to be accelerating in They're not just going to have a centripetal acceleration, they're also going to have an acceleration this way to like speed them up. Okay, so remember that's this expression. So now they're going to have a tangential acceleration and this radial acceleration. We're worried more about this radial acceleration right now, though, because that is what is required to keep them moving in a circle. And the question is asking which one is going to fly off, which one is no longer going to be moving in a circle, right? So please, please, please do not get please do not get the two accelerations confused. Every object moving in a circle will have centripetal acceleration. Only objects that are moving in non-uniform circular motion, where omega is changing, where the rotational speed is changing, only those are going to have tangential acceleration. This expression right here, omega squared r, is centripetal acceleration. Alpha r is tangential acceleration, where alpha is a change in omega. Okay, please, please, please keep that all straight. Anyway, we've talked about this a million times, but you can see that because A is farther away, for any given omega, it's going to have it's going to require a larger centripetal force, just because the r is bigger. A and B will always share the same omega. Even if omega is changing, it's going to change the same for both of them. So we're worried then about which one has a bigger r value. That's going to require a stronger centripetal force. That's going to require a bigger force of friction to keep the thing moving in a circle. A is going to fly off first. All right? So hopefully this is reminding you of the skills that you guys need to have. You need to have all this rotational kinematic stuff down. And you need to be able to calculate those I values. And let's move on to new things.